Hello everyone, Assalamu alaikum. Welcome back to my channel. If you haven't subscribed to my channel, just click the button and hit the bell icon so that you can get in touch with the latest content. Now, in today's video, we are diving into the Cadence Virtuoso, which is one of the most powerful tools for custom IC designs. This is lab 2 of our VLSI Lab series, where we'll be introducing you to the Virtuoso environment, creating your first inverter schematic, and performing some crucial simulations. So, if you're ready to take your VLSI design skills to the next level, stick around. Now, the first step is to open your Virtuoso environment. For that, just open your terminal window from desktop and type Virtuoso and ampersand, and the following window will pop up. So let's familiarize ourselves with the Cadence Virtuoso environment. When you open Virtuoso, you'll see the main window, which includes the Library Manager (CIW), or also called as Command Interpreter window, and the Virtuoso layout and schematic editors. This might look overwhelming at first, but don't worry, we'll break it down step by step. Now this Virtuoso Command Interpreter window appears at the bottom of the screen. From the CIW menus, all the Cadence main tools, online help and options can be accessed. In the window area, all kind of messages generated by different Cadence tools appear. Now let's talk a little bit about custom IC design flow that we will be using throughout this lab series. Now there's a figure in front of you. Let me explain what is going on here. First, a schematic view of the circuit is created using Cadence Virtuoso schematic editor. Then the circuit is simulated using Cadence Analog Design Environment, or as we call it, ADEL. Different simulators can be employed, some sold with Cadence software, for example, Spectre, some of them from other vendors, for example, ASPICE, if they are installed and licensed. Now, once the circuit specifications are fulfilled in simulation, the circuit layout is created using Virtuoso Layout Editor. The resulting layout must verify some geometric rules depending on the technology, which we call as design rules. For enforcing it, a design rule check or DRC is performed. Optionally, some electrical errors, for example shorts, can also be detected using an electrical rule check, which we call as ERC. Then the layout should be compared to the circuit schematic to ensure that the intended functionality is implemented. This can be done with the layout versus schematic or LVS check. All these verification tools are included in Shora software in Cadence. Now finally, a netlist including all layout parasitics should be extracted using Quantus QRC tool, and the final simulation of this netlist should be made. This is called a post layout simulation and is performed with the same Cadence simulation tools. Once verified the layout functionality, the final layout is converted into a certain standard file format, for example CIF, etc., depending on the foundry using Cadence conversion tools. Now let's hop on to learning fundamentals of PDK and adding PDK library to the library manager. Now, Cadence is an electronic design automation, or as we call it, EDA environment that allows integrating in a single framework different applications and tools. Now, allowing to support all the stages of IC design and verification from a single environment, as we have just seen. These tools are completely general, supporting different fabrication technologies. When a particular technology is selected, a set of configuration and technology related files are employed for customizing the Cadence environment. This set of files is commonly referred to as Process Design Kit, which we term as PDK. Now, how to create your library and attach it to the existing technology. Now, all the entities in Cadence are managed using library, and each library contains cells. Each cell contains different design views, um, containing subdirectories, each one containing files. Thus, for instance, a certain circuit, for example, an inverter, can be stored in a library, and such library can contain different logic blocks stored as cells. Each block contains different views. Now, there are usually three types of libraries. Uh, Number one is a set of common Cadence libraries that come with the Cadence software, containing basic components such as voltage and current sources, RLC, etc. The second one is the library that comes with a certain design kit. For example, we will be using GPTK090 in this lab, and that are related to a certain technology. For example, transistors with a certain model attached, etc. Then there are user libraries where the user stores its design. These design employs components from the Cadence or design kit libraries, which we will be creating right now. Now, it is recommended that you use a library to store related cell views. For example, use a library to hold all the cell views for a single project. In our example, we are going to create a new library for our design and attach it to the desired technology library. In order to do that, in the CIW, execute file, then click on new, then click on library. The new library form appears as follows. Now, in the name field of the new library, you can type the name of your library, just name it however you find easy. Then select attach to an existing technology library and click OK. Now, this attached library to technology window will appear. Select GPTK090 technology library and click OK. This will be the technology chosen for your design that you will employ eventually for fabrication. Now, all the designs are made in this library are technology dependent. For example, the schematic MOS symbols have by default the model for this technology, the available layout layers corresponding to this technology, etc. Now, in the CAW, following message will appear or something similar to this one. Now, let's create schematic. In this exercise or in this lab, you will learn how to enter simple schematic and run a simulation to perform timing simulation of an inverter designed using GPTK090 technology. We will not be covering the layout part in this lab, it will be covered in the later lab. For creating your schematic, in the CIW window, execute file, then new, then cell view this time. Now set up the new file form as follows. So for library, you will select the library you just created. Then for cell, you will select the inverter or write inverter because we're creating the schematic of an inverter. Then in view, you will select schematic, then type schematic and application open with, and you will select schematics. If it is already selected, then leave it as it is. Then click OK when done. The following window may appear. Now a blank schematic window for the inverter design appears like so. Let's add an instance to the schematic. Okay, so we will add instance of NMOS and PMOS. So to create an instance, you can execute create then instance in Virtuoso schematic editor window or simply use shortcut key I. The following window will appear like so. Then click browse to select the library component. Another window will show up. Choose library, then select GPTK090, which technology we are using, then cell NMOS 1V, and view will be symbol. Note that while you are doing this, the add instance form is getting updated as well. Make sure that the view name field in the form is set to symbol. After you complete the form, move your cursor to the schematic window and click left to place the component. Similarly, add PMOS 1V cell. Now we can adjust the sizes of the transistor by editing instance properties. Left click on the NMOS to select the component, then press Q to modify its properties, or in the schematic editor window, execute edit properties and then object. You will update the library name, cell name, and the property values, and just like I'm doing here. Now for NMOS, I'm fixing the width to 240. This is 2 times the minimum channel width. And for PMOS, I am selecting the width to 480 nano. Um, so I'm setting the total width for both of these transistors. And once I press the tab button, the finger width will automatically update. After doing this update, click on OK. If you place the component in the wrong location, select the component and press M on the keyboard and move it to your desired location. After entering the components, click Cancel in the Create Instance form or press Escape, keeping your cursor in the schematic window. Next, we will instantiate power nets, VDD and ground, from the analog library. For that, execute Create and then select Pin. Or alternatively, you can press P on the keyboard. Then Add Pin form will appear. Enter the name of the pin, for example, in. If it is in logic pin, the direction of pin should be selected. For example, you can also write input or output, etc. Add all the pins in and out to the schematic. For inverter, gate input pin, for example, in is the input pin, and output pin, for example, out is the common node between the drains of NMOS and PMOS. So select direction property as input for in and output for out. Then we add wire to the circuit. For that, select add and then wire, or simply press W key to enter wiring mode, or you can press escape to exit. It is a good practice to periodically save your work by clicking on click check and save button. Now you can also save your work from the drop down menu, file, and then save. The final schematic looks something like this. Also, you need to check CIW for errors. If there is no error, you should see the following message. Once we're done with the schematic, we will create the netlist and simulate using Spectre. For that, In the schematic editor window, execute launch and then select ADEL. The following window may appear. Now set up the model libraries by executing setup, then model libraries. This model library setup window will appear. Click twice on the file name given under model files, global model files. An ash colored or gray colored button will appear like so. Click on the button and choose model file window will appear. From this, you have to select gptk090 mos underscore mos dot scs file like I am selecting here. Then click open. In this model file, there are models to simulate various corners like fast fast or FF, fast slow FS, typical typical TT, etc. These are called process corners depending on the speed of the MOS transistors. We will choose the section typical from the section scroll bar and select this section TT S1B. I'm doing this for typical, but you can process each corner accordingly using the same rules that we have just done. This will enable us to use the TT model of 1.2 volt MOS transistor. Then we will click OK. Now execute setup, then stimuli to assign signals to pins of the inverter. In setup analog stimuli window, select global sources. Now you can see the global power net VDD. Click on enabled, select DC under function and voltage under type. The filled up form for VDD will look like something like this. Then click apply. You must not click OK right now. Clicking apply will enable this pin. So you must click apply. For input pin in, we have to set the pulse waveform. So for setting this signal to input pin in, select inputs in setup analog stimuli window. Click on enabled, select function pulse, type voltage. Parameters for pulse source will be something like voltage 1 is equal to 0 volt and voltage 2 is equal to 1.2 volts. I'm doing this for my application. Period, I'm giving the period of 40 nano. Delay time, I'm giving it 3 nano. Rise time 3 nano. Fall time again 3 nano. And pulse width, I'm giving it a 20 nano. Then click apply and then click OK. First you have to click apply and then OK. Now choose the analysis to be done from analysis and then select choose. Select transient or TREN analysis to be done. Provide 100 nano as stop time. Analysis is trans and stop time is 100 nano. Accuracy defaults to moderate. Then click OK. Now select the output to be plotted by executing outputs and then select to be plotted and then select on the design in this ADE window. Schematic editor window will open. Then select out and in to be plotted and saved. When you select them, you will see the colors being assigned to these pins, like so. Your colors may vary. Your analog design environment window should now look something like this. Now, before closing the Virtuoso analog design environment window, it is a good idea to save the design settings in a state file so we can load it up next time. To do this, execute session and then select save state and save state name in the save as field as state inverter. Next time you run Cadence, you can simply load the simulation settings from this file and you don't have to set up all these things all over again. Now run the simulation by executing simulation and then select netlist and run in the ADE window. The simulation will run and output will appear in the Virtuoso Visualization and Analysis Excel window as shown. Now finally, We are going to separate the plots in two subgroups because this is we cannot extract anything from this one, so we have to separate these graphs. Click on the following icon for splitting the graphs. The final plot should look something like this. Now, three main timing parameters are associated with CMOS devices as rise time, fall time, and propagation delay. How to measure propagation delay, which is important parameter that we measure using this waveform calculator. Now, waveform calculator can be used to perform many different measurements and transformations on the waveform displayed in the waveform window. This includes computing the average of the waveform, for example power, over the entire length of the simulation or in a given period of time. Execute tools, and then calculator. In Virtuoso visualization and analysis Excel window, this Virtuoso visualization and analysis Excel calculator window will pop up like this. You will select VT, go to schematic editor window, and click on the input node in an expression, for example VT, and then this type of expression will appear. Copy this expression in this function panel, select special functions, and then select delay. The following window will appear. Put the expression previously obtained in this field signal 1. Do the same for output signal to fill the field signal 2, like so. Now fill up the rest of the form as follows. Then click OK, and the following expression should appear. Click on evaluate the buffer icon. The propagation delay in seconds will be displayed in the window, like so. Now let's try to measure rise time and fall time using this same waveform calculator. Open the delay function window under waveform calculator in the same way that we followed previously for propagation delay measurements. This time both signal 1 and signal 2 will be VT out. Threshold value 1 and 2 should be 0.12, that is 10% of 1.2 volt supply, and 1.08, that is 90% of 1.2 volt supply, which was set by me for 10% to 90% rise time calculation. These values should be swapped for fall time calculations as well. So I'm showing you the rise time calculations. For rise time or fall time calculation, both the edge numbers must be the same, like I'm setting. The edge types should be rising for rise time calculation and falling for fall time calculations. Now your window should be appear something like this after filling the form. Then click OK. After filling the form, the following expression should appear, and this is your calculations. The same procedure can be done for the other fall time calculations. Now what you can do is resimulate the circuit using fast corner or slow corner, using the same procedure, repeating the same procedure, just you have to select different process corner. Last thing that we need to do is power measurement using this same waveform calculator. To do this, make sure that before running simulation you select outputs and then save all option in this ADEL window. Save options window will appear. Under select power signals to output options, put a tick mark in all options, then click OK, like so. Then simulate the circuit as usual by executing simulation and then netlist and run. Execute tools and result browser in the ADEL window. A result browser window will appear to the left side in the Virtuoso Analysis and Visualization Excel window. Double click on Tran from the signals, uh, then double click on Power, PWR. The waveform display window will show this power. This is instantaneous power consumed by the whole circuit along with in and out signals. Now open waveform calculator window again. The calculator window will appear like you have seen before. Make sure the wave and clip options are selected. Now switch back to the waveform window and left click the mouse once on the power waveform. Then switch back to the calculator window. The buffer window should be filled in as follows. Now select average from special functions menu. The buffer will now look something like this. Click on evaluate the buffer icon and average power dissipation in that time window will be displayed. Okay, like so. And that's a wrap for this lab. We have covered a lot today, from setting up Cadence Virtuoso, creating an inverter schematic, performing transient simulation, and analyzing power and delay across different corners. These are foundational skills in VLSI design, and you'll be using them throughout this lab series. Thanks for watching. If you found this tutorial helpful, make sure to give it a thumbs up and subscribe for more content like this. And don't forget to check out the next video in the series where we'll be diving even deeper into VLSI design. See you in the next one.